I, I have a really, really difficult mission. I'm the only thing that stands between you and lunch. My bottom line is not that original, but I would still say it because it's my vision, and I'm a little kid from a ghetto neighborhood in Jerusalem. So my little vision is that in the next 100 years, we should devote also to the understanding of the human brain, to curing of the human brain from depression, from Alzheimer, but also to the understanding of the amazing abilities like individual differences, imagination, and creativity. So I want to give you two very quick examples of how the brain is doing mental imagery. And I would like to start by a beautiful theory that proved to be very strong for many, many years by Koslin, and that is that the same areas and the same mechanisms that we use for perception are used for mental imagery. So if we hear music and imagine music, if we see an apple and imagine an apple, we must first experience it during our first years of life, and then the same neurons in the same areas will work when we will imagine. When I started to think about this problem, I thought this is a beautiful theory, but there is one little problem. If this is true, then we would have very strong difficulty to separate reality from hallucinations. There is also something unique in the brain that has to do something to do with imagination. And by coincidence, or not by coincidence, it happens to involve also this area that Sandra was finding this unique fingertip in Albert Einstein's brain. And by one little, actually not little, this is the main thing I was doing, one of the projects in the last 10 years, and this is to use the power of mental imagination in congenitally blind and late blind to create an image in their mind eye using music. It sounds a little bit weird, but it's a little bit like dolphins and bats are behaving. When there is vision, they work with vision. When not, they are starting to use sheets of sounds. We take visual space in this project and convert it into a time and music domain in a way that maintains shape, location, brightness, and even colors in the image, all in the music. So I took the liberty to take Albert Einstein's very interesting equation. You see a visual rendering of a pentatonic scale, which is Bobby McFerrin have a beautiful TED talk, 3 minutes, showing how it's universal. Everyone can learn and use this scale. And on the x-axis is time. So you would, for example, for a smile, you would hear something like dee 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 dee. And for a sad face, you will hear something like do 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 do. And what we are doing is we are teaching people that never saw in their life to use mental imagination to imagine what is in front of them. For example, one of our blind individuals was using it to teach her kid, her sighted kid, to read and write. Now, what is even more amazing is what happened in the brain. We imaged some of our volunteers, and what we found is that in any individual that we were studying, we found that the brain is actually doing the reverse algorithm, taking sounds and transferring them into images, but using the system that never saw, exactly in the same places. This is what you see in this movie, that the information flows into the visual system, and this is where they build, using their mental imagination of a system that never saw the images and being able to recognize facial expression or teach their kids to read. The second example is related directly to Einstein, and when Albert Einstein was forced to summarize the general theory of relativity, which some says is the most beautiful theory in the history of science, in one sentence he said that time and space and gravity have no separate existence from matter. This is one sentence summary. You know, the media like to get one sentence summary of the theory and one sentence of how he got to think about it. He said, the first time I started to think about this, but by doing what he would use to call this Gedanken experiment, this thought experiment, which involved mental imagery. But it's really unique because what he was doing a very special type of imagery. Because imagery, you can say, okay, I want to image this apple. I close my eyes and I imagine it. But what he was doing mental imagery of his body. And he was transferring his body in relation to space and to a beam of light. And then imagine himself riding this beam of light and trying to think about how this beam of light will look, and he came up to the conclusion that there is a problem, that he would observe such a beam of light as an electromagnetic field at rest. And this bothered him for many years. Of course, imagination is not the only thing. You have to acquire knowledge in mathematics, and he then worked many, many years to develop the equations. But this was the key, this mental imagery of exporting, thinking about his body and exporting him. What do we know about this brain structure that supports such a mental experiment? We have a little bit of evidence here and there. We know so little about the brain, but we pick up some clues. And the first clue came from here, from Montreal, from Penfield, which was a very important guy in the Montreal Neurological Institute. And he was working with epileptic patients, trying to find the source of epilepsy and destroy it so people would not collapse and risk their life. And he found this place that later became the area that he discovered, the Penfield homunculus, that if he stimulates one part of the brain, we move our feet or have a feeling on our feet, like water spill on our feet, and you go a little bit lower, and it's in our hands, and you go a little bit lower, so we have a map, a topography in the brain that he discovered. 17 years later, he actually found that there is one homunculus to the motor system to move, one to the somatosensory. Actually, he found two other homunculi, and after he sent his last paper to print, he asked it back. He said, maybe there is another one there. So fast forward many years later, we use these computational neuroimaging methods that I won't have time to get into. But what is amazing about imaging is that with one experiment, you see not just where you have the electrodes. Penfield had the electrodes only where there was epilepsy. He didn't put them in the entire brain. So we could see in 10 minutes the entire brain now. And we actually found the original homunculus, the hypothesis homunculus, and another 10, which we have absolutely no idea what they are doing. But this is all related to the body. What about mental imagination of our body? And what about mental imagining our body in relation to space? This is what Albert Einstein used when he was thinking about riding in this beam of light in space. So we started to do this type of experiment recently, and this is, actually I'm saying this is the first time I'm showing this data. In this experiment, people are either doing mental imagery of their body or thinking about their body in relation to space. And we find this beautiful map of mental imagination and its relation of the body into metaspace, not in Penfield homunculus, but in a different area. And by mere coincidence, we were sitting in dinner. I was invited to be a Brain Awareness Week speaker from Israel in Canada. I had an amazing time last March, and we started to speak and started to independently analyze this data and found that it overlapped the same area that had this unique fingerprint in Albert Einstein's brain. So I think I would finish here and say that brain and mental imagination, the journey is only began. This is going to be the century of the brain, and the brain is going to be the final frontier. So I want to thank you very much. Actually, the people that are doing this work is these Hebrew University students, and I want to thank them very much. But I also really worked last night on this presentation. So thank you, have a great lunch, and enjoy.
Thank you. Thank you, Amir.